Vahab is going to talk about one very important, so to say, I would say, I would not say reinvented. This is not a completely new aspect, but it is something that's becoming very important, and that's privacy preserving data mining. And we are very happy that although he's extremely busy going back and forth, I think he has the oversee in New York and in Zurich. And I also want to ask him why Vahab Zurich and why not Germany? Why not Darmstadt? Or yes, what do you want in Switzerland? Everything is expensive. They are not as efficient as we are. I can prove it to you in terms of publications and other things. I don't know why you guys are going there. Anyway, I'm really happy that he accepted our invitation. And please, Vahab, the stage is yours. We are really looking forward to your talk.
Hello, do you hear me?
Yes.
Thanks a lot for having me. Yeah, I'm going to talk about privacy preserving data mining. The focus will be on the clustering aspect. So I come from Google Research, the algorithm optimization team. We have teams mainly for like in New York and Zurich. Actually, Zurich is the main office in Europe, and like we have folks even in Spain. In Germany, we do have also like an office that has potential to hire in these areas. So bear with me. Maybe the focus of the talk will be on academic research. Maybe before I dive into the talk, I'll tell you a bit about where I come from. So I lead this new, basically algorithm optimization team that spans like different areas. The three main areas are what we call market algorithms, graph mining, and large scale optimization. So we have different aspects of data mining in the graph mining library that we provide. Many like market related problems. Privacy becomes like an important aspect in like the next generation of advertising that Google is going to provide. So it has become more and more important for us. And yeah, so like we do interdisciplinary research in these areas, in particular on the graph mining side, which has become more and more related to the privacy. We are building, the goal is to build the most scalable graph analysis platform that can be also used across Google. And like we are trying to also open source more of it through Google Cloud. Yeah, so it's widely used at Google across different platforms. We develop scalable algorithms that can handle graphs with billions of, like tens of billions of nodes and like trillions of edges, let's say. And the applications, yeah, like I have some examples here. Just to give you one more specific example that may be more related to this workshop, a canonical use case is in spam, fraud, and abuse detection, where we use label propagation on graphs to detect bad actors from basically some known like bad actors. So we predict new labels by finding or discovering relationship between different actors. We also use graph mining to detect anomalies or through clustering. Like basically we identify dense structures that are that are unusual and maybe malicious. But the new challenge in doing all of these is to balance between the privacy and safety of the user. So when we want to provide these tools, we have to like mine the data and come up with like relations between users and so on. And privacy aspects have become more and more important over time. Again, I'm not going to talk about like basically all the related sensitive problems here. I'm just giving you like a high level motivation, and that will motivate the topic of the talk that lives on the intersection of graphs, clustering, and privacy. So one like general idea, if I want to give you how we use clustering and graphs in protecting privacy, I can say that basically in many cases, we are trying to protect revealing the relation of users to other entities. For example, users visiting a website. So that can be modeled as a bipartite graph between users and the domains or websites they have visited. And this becomes very relevant for projects like deprecation of third-party cookies, which is like a central, basically, application of this area. One example of how we use clusters is basically we, instead of analyzing the data on users, we analyze the data on clusters of users where each cluster is of size at least k, and this way we are anonymizing the data. So we never look at the data, or like we don't share the data with on an individual basis, but like we basically share it at an aggregate level using basically a clustering technique. So this is just to give you a very high level idea, and I'll elaborate on this. So the outline of the talk now is going to go over two applications of clustering and enforcing privacy. The first application is in providing anonymity in what we call interest-based advertising. And the second application is for providing clustering in achieving better label differential privacy. I'll also talk about basically how we develop new algorithms at scale to deal with these problems. If I have time, I'll also have a couple of slides on the topic of how to protect users' privacy in a social network or social graph type application, and like how to do it in a federated way, like for on-device public-private data mining. Let us start with the first part of the first chapter, which is about mean size clustering for private interest-based advertising. This is based on a recent paper appeared at KDD. So the story of advertising, online advertising started in 1994, where we've had the first online ad around 2000, like before 2000, like search ads showed up, and online advertising has become like a $100 billion basically, or yeah, like a big industry already. So in 2020, what we have is display ads and like a lot of ads personalization. And this is a big industry. It's not like many companies basically depend on it, and it basically funds the free web. The story of interest-based advertising is basically related to providing very like relevant and personalized ads. This interest-based advertising allows advertisers to reach different audience of a specific interest. It does provide a better ad experience for users, and like as a result, publishers who fund their content using this data basically charge a premium for interest-based advertising. What they call cost per click or cost per impression is much higher in this space. So it does, but how is it enabled at the moment? It partly, or a big part of it, is enabled by what we call third-party cookies. But these third-party cookies also incentivize different players to track users. Let's elaborate on this a little bit. So when a user basically visits a website, I mean, there are like third-party companies that basically the cookie ID of the user is basically logged in an ad tech. So we know that a user, for example, visited different domains. We know like the same user has like some interest in certain domains. Now in the ad serving system, when this user and the user profile is provided to the ad tech can use this information and come up with campaigns that are basically that have similar features to the domains that the user has visited in the past several days, maybe. The question that we are trying to tackle, it's a $1 billion, $100 billion question, is how can we provide users with good ad experience and like fund web through this interest-based advertising without letting basically without providing a venue for analyzing the detailed browsing histories of users. So the observations that help us like go toward designing a better system is basically that the first observation is that advertisers don't need to know like the identity of the user, they need to know the interests of the user. So that's like one level less privacy violating. Browsers compute user interests. And instead of tracking the identity of user and what they have visited, maybe browsers can only provide a venue or like API to like to provide user interests. So one idea is instead of providing basically like user profiles, browsers provide clusters of users. So browsers themselves like cluster users and share the cluster IDs with ad tech companies. That's the idea behind at least the paper I'm presenting here. So the goal here is that the users with similar interests are going to end up in the same cluster. So basically what happens is that the cluster ID basically shows the interest of the user because the users are basically not tracked, but the clusters of users are tracked. And like the way that the anonymity is enforced is by making sure that the clusters have a minimum size. So the problem that becomes relevant here is clustering with size constraint. So like in summary, ad tech companies will build cluster profiles and not user profiles. But now the question is, how useful are these cluster profiles? And that's the question that we're trying to answer in this paper. If I want to tell you the components of this, what we call private interest-based advertising, it's the user representations and user clustering. So for the user representation side, what we know is that each user has a profile that basically for each domain that they have visited, the domain itself has a feature vector with maybe some weights. Like we know that New York Times /art is like news with some weight, has like arts with some weight, and so on and so forth. So we can aggregate these, we can aggregate this information in like a vector of feature with weights, and that becomes the feature vector for those users. So now, how do we cluster users? We take these feature vectors, and the goal is to do this clustering in a completely decentralized way from browser side even. So one idea is to use like hashing techniques or sketching techniques. So like this sim hash, for example, technique, like easily puts users, I mean, like it takes like a long feature vector and it projects the these long feature vectors to like lower dimensional like feature vectors, and then we get like basically clusters of similar users. But this idea itself tend to generate unbalanced clusters, so the size constraint is not enforced. Let's yeah, so one idea to take the sketching technique and make it more size constraint friendly is to do the projection and take different basically steps, but what we call prefix, by using prefix CLS, like locally sensitive hashing, we can keep track of the size of the clusters that they are ending up with and stop basically dividing that subspace more if the size constraint is violated. So we can do it on up to the point that the size constraint is met, like we have a minimum size constraint. So that's a clean, simple idea. The other idea is to do what we call hierarchical clustering of all users and then go up in the hierarchy. So for the hierarchical clustering idea, we use a scalable tool we call affinity hierarchical clustering that tries to keep the heaviest edge, like when we build the nearest neighbor graph among users, and then it puts them together, and in a parallel way, it keeps like adding clusters together. And but what we do is we add also size constraint to this, so this is based on like a recent paper we had, and like an internal affinity hierarchical clustering tool that can handle very big data sets. So what we added to this is a size constraint that when we go up in the hierarchy, we stop, we go until like we satisfy a minimum size constraint. So these are the type of clustering techniques. For evaluation on public data sets, we take a number of like data sets, like a song data set, a movie lens data set. Then we want to see how good is this clustering in terms of providing a utility privacy trade-off. For the utility, we look at the average cluster similarity within a cluster. So we track how similar are the like nodes in the same cluster. For privacy, we track the percentage of users that are basically covered by clusters of a minimum size. I mean, ideally, this has to be 100% for the purpose of the paper. We reported like this specific privacy number. So what we observed was that, first of all, SIM hash and prefix LSH provide a much better, basically, utility privacy trade-off. So if we look at the like the privacy dimension and the like the precision or the similarity between clusters, we see that, I mean, we don't draw the random here. Actually, we'll see it like in a later slide, but it's like much lower. What we see is that, yeah, like the decentralized algorithms like prefix LSH provide a good improvement over random, but the centralized one, especially the affinity, provides like much better trade-off. Metis is like a known like library outside Google, so like we also use this as a baseline here. So we also looked at the as data itself. Those are for public data. So we have a specific way of measuring the quality of basically the clusters that we build over the third-party cookies. The baseline itself is the profiles that are built on the third-party cookie itself. But then we have a specific methodology to basically report the precision of the clusters and the coverage of or like the recall of the clusters. We have precision because we are like putting users together. We have to see how similar the users are or not. And recall is what percentage of data we can cover with clusters of size at least something. So what we observed was that like over like a random clustering, for example, these prefix LSH and the SIM hash techniques provide a much better precision and recall, and the centralized algorithms also provide an improvement. But actually on the real data sets, the decentralized algorithms were good enough or like are within a margin of the centralized algorithms. So, and in reality, we do need the like the highly decentralized algorithms to be able to provide them on browser side. So we have like basically deployed this as an experimental solution. So in summary, we just talked about how to get interest-based advertising with good privacy utility trade-off. The solution we provide is a clustering solution that seems to be a viable solution to provide a good like a utility trade-off at least. While centralized algorithm provide the best utility, in browser clustering is very competitive. One question that one can ask here immediately after this thing is that how about other notions of privacy? So here we are satisfying what we call k-anonymity. So like we are making the data anonymous, but privacy experts know like the issues like with still tracking users with k-anonymity. What we would like to understand is like how can we also provide a measure for user re-identification, fingerprintability, and also differential privacy. So these are active areas of research for us. For example, in the area of differential privacy, we know that empirically speaking, on many big data sets, the K, so like if we fix the utility, if we want to get some utility, the K that we can provide in like a K anonymity solution is much more favorable compared to the epsilon that we can provide. Or like maybe I should say we can achieve the same utility for high Ks and like low epsilons. So that's an indication that maybe DP is not like the right solution, is not the best notion because we can't provide the right utility. Also in a theoretical sense, we have a stylized model and like an information theoretic lower bound for achieving low epsilon DP with constant factor utility in this area of data sharing. So that's like maybe like a negative observation about differential privacy, like a more general differential privacy for interest-based advertising. At the same time, we try to provide like to understand what can be achieved in differential privacy, which is the most you know, like popular notion of differential like a privacy out there, at least in the academic literature. So the next part of the talk is going to go over how we can provide label differential privacy via clustering, and that's the machine learning settings. I don't know if so we take questions at the end, yeah, like can you confirm, because I have different sections in the talk. We can also take some questions once in a while because I'm switching topics a little bit. But, yeah, I don't know if nobody stops me, I'll continue. Otherwise, because I can't see you, I'm yeah, like I'm looking at.
Yeah, we have a Q&A session at the end.
Okay, thank you. So for the label differential privacy side, first I can motivate the setting, what we call label differential privacy. So the first thing to observe is that the machine learning algorithm takes as input a training data set and outputs a predictive model. So what people call differential private machine learning algorithms depend only weakly on the training examples. So like a most popular DP machine learning algorithm is what's called DP SGD. DP is stochastic gradient descent, and it's like widely used here and there. But the key premise of the differential private machine learning is that we don't have to protect basically the part of the data that's not sensitive. Let's say the statistical inference is not like a privacy violation, they say, but basically what boils down to like more practical matters is that if we know that smoking causes cancer, if you're a smoker, that's not a private, that can be one thing that is not private. I mean, this is just an example. Maybe it's not the best example. This can become also like privacy, like sensitive, but maybe the part that you have cancer is like a very private. Maybe like there are different elements of the data. So you don't have to maybe protect everything that's like publicly known. But yeah, like I have maybe a better example later on. So like basically because like if we want to enforce full differential privacy constraint on the whole end-to-end like data sets, the problem becomes completely infeasible. What people are like doing is to try to only keep basically part of the data that's like need to keep private, but not the features that are maybe publicly known. So an example is, for example, hospitals would need to predict cancer risk using patients' like information, age, weight, gender, and so on. But some of these features are public, and maybe users, we can get users basically willingness to share that part of the data. So that becomes less privacy sensitive. But we know that hospitals are also like not, I mean, nowadays there are like many ML experts everywhere and hospitals, but maybe they want to share the data with like a research institution, how to do this in a way that they can protect the sensitive part of the data. So the problem statement in a machine learning scenario here is that we have a training data set that's drawn from some distribution and a loss function that evaluates the hypothesis. So we want a mechanism that takes as input a training data set S and outputs a noisy training data set S prime and a proxy loss function L prime that satisfies the privacy and utility performance trade-off. So how does differential privacy evaluate like the privacy part? We say if two training data set S1 and S2 only differ on one label on the data, then the mechanism output on these two should differ distribution-wise only like with the ratio of an exponential in epsilon. So this is the property that we need to satisfy in order to make sure that for any two data sets that only differ on a label, we should not output something that's drastically different and can be identified as that one label that we want to protect. On the performance side, we want to make sure that what we output is closely related to what basically is provided to us. So the training data sets don't provide a drastically different loss function for different machine learning algorithms. So in particular for label differential privacy, we have, I mean, this is just a recap of what I just said. We want to only protect the labels. Let's go over the mechanism that we use on an example to clarify what we mean. So what we do is we do an unsupervised clustering algorithm on the training examples using the feature vectors that have similarity, and they can give us a sense of how similar things are. Then we do label randomization within clusters. And then we do like some corrected loss for bias corrected loss. Let's go over an example. So let's say we have this data set, the images, those are the features that are public, but the labels are, let's say, private. So what we do first is to cluster training examples using only features, and we ignore the labels here. So remember, we want to release this data set with labels for experts to develop better machine learning algorithms, but we don't want to reveal the labels. We want to reveal the labels in particular in a basically private manner. So what we do is we first cluster the data based on the features, and then so like here we have made some mistakes in the clusters, perhaps. Hopefully there are no twos in the tree cluster and so on, but there may be some mistakes. So what we do then is to basically for some randomly chosen labels, for some randomly chosen examples in the training data set, we replace the true label with a noisy label. So here, for example, we change like these like red labels, but we take the noisy label drawn from the same clustered label distribution. We don't put like an arbitrary label there. We put like a label from the same distribution of labels on the same cluster. So now we output the noisy training data set to the machine learning expert, and a proxy loss function that try to compensate for the bias that we introduce using these basically label noise. So like this is like an outline of the algorithm, just summarizing what I just said in pictures. So let me skip this. So now we want to prove, or what we prove is that our mechanism performs well when these clusters are number one, large, and number two, coherent. Let me try to define what coherent means. So we have a measure of coherence that tries to say like basically how much we deviate from the distribution, like on each example, how much we deviate from the distribution on the labels on the same cluster. So like this measure phi says if we have like a smaller phi, we have more coherent clusters because we have less label distortion when swapping the labels within the same clusters. So example of clusters with good coherence are clusters that have 50-50% label distribution, but each feature vector in the cluster has label distribution 49% to 51%. And but if the label distribution on each feature vector is like very much bipolar, then it's not a good coherent cluster. So in theory, what we show is that the differential privacy bound, or like what we call the excess risk that we can provide here, basically is asymptotically optimal if either the clusters are large or the size of the clusters are big. So that's like the summary. But we do need basically these high quality clusters to get these like tight asymptotic bonds. So like this term is an additional term that should disappear as a function of the quality of the clusters. So we also have empirical studies of this clustering algorithm. For example, for this one, we use a k-means clustering algorithm with some k. And what we show here is that DP, like we compare, for example, the DP SGD as basically a baseline, and also like the baseline that changes labels uniformly at random in general. So we see that we get a much better utility privacy trade-off. So here now the x-axis is the privacy parameter epsilon in terms of the differential privacy parameter. So the blue line corresponds to what we call cluster randomized response mechanism. Okay, with this, we also have some other ways of validating that these clusters are meaningful and useful for utility. We also provide a hardness result that shows that in certain settings with what we call label association problem, the bounds that we provide in terms of the trade-off with the quality of the cluster and the cluster size is almost tight. So in some sense, it's tight. It also shows that if you want to go to what we call from item level privacy to user level privacy, the problem becomes much harder. There are many interesting open questions here. One is, how do we get the large and coherent clusters? So here for the empirical study, we use some simple like k-means algorithm with some size constraint, but we can formalize this problem more formally and like provide better algorithms. Actually, that's something that I'll mention in the next slide, in the next couple of slides. Then basically the question also is, can we put this idea on top of DPSGD and get a better like algorithm by combining the two ideas? So now I want to give you like a summary of what we call parallel large scale minimum size clustering algorithms. This is a joint work with my colleagues, and I made Pelin, who is the more junior student on the paper, because he did a big bulk of the work, and the slides also come from him. So just a recap on the motivation behind minimum size clustering, because I want to tell you like a bit more on the algorithmic side. We just went over two applications of one is in achieving K anonymity, and one was in achieving improved label differential privacy. So yeah, like the K anonymity specific application was in interspace advertising and so on. So just in terms of application, we know why we're talking about minimum size clustering. We know that there are many scalable algorithms for what people call balance partitioning. For example, we have a couple of papers about how to get like balance partitioning of big data set at scale. But when we want to enforce the minimum size cluster size, and that's like a small minimum cluster size, the known algorithms are like very limited. What we do is we basically study this problem of R-gather, where we have basically endpoints in a metric space and a parameter R. So we want to partition the data set into clusters of size at least R, and a set of centers for a center for each cluster. So the goal is to enforce the minimum cluster of size at least R and minimize the maximum radius of the clusters. What we want to achieve, however, is a massively parallel all-gather clustering algorithm. So this is what we call massively parallel computation model, or MPC model. This is an abstraction of the MapReduce or Fung model, where we take the data, we divide it into K machines or P machines, and then we do some analysis, and then these machines communicate with each other. And like, we want to minimize the number of rounds of communication, and also make sure that the space per machine we use is limited. Also, the congestion on the like communication is bounded. So it's a formal model of computation. What we show is a fully scalable, massively parallel computation model for this R-gather problem, and also actually a fully dynamic, like a scalable, like with other extensions, also like a dynamic algorithm. So I think the specific details of the algorithm may not be maybe out of scope for this talk, but it's good to know that we use the approximate nearest neighbor search, locally sensitive hashing again, and we compute first what we call a maximal independence set on like the graph that we build, like when we build the nearest neighbor graph is G, then like we build like the square, or basically the maximum independence set on G to the 4. And then we use the maximum independence set as potential or candidate centers, and then we do like post-processing and local search to improve it. And we can formally prove that this is a good approximation, like a constant factor approximation to the best solution, and it also runs in logarithmic number of rounds, actually much better than logarithmic log to the epsilon number of rounds, and we use only a sublinear space in terms of the number of edges on each machine.
Just to let you know, 5 minutes left for the talk.
5 minutes, okay, good. That sounds good. So here we also implemented this algorithm as a like in Flume and distributed hash table service, and that will be like a different topic of like a so like, well, I just want to emphasize that this is an algorithm not only in theory, but also we implemented it, and we also report in the paper some comparison to the set of algorithms that I mentioned at the beginning, affinity based. So it improved over those, but maybe not by a large margin. But this is also like theoretically provable for any data set. So we are also like trying to improve the empirical performance of these algorithms. I guess I'm like done with the main part of the talk, where we talked about different clustering algorithms that can be used for privacy enforcing settings. I do have a couple of slides on this topic of what we call on-device public-private graph model. But I think I mentioned this one slide and let you read the papers. We have a number of, like a couple of papers where when we have a data that is represented as a graph, or like it's actually a graph over users, but they sit on different devices. We want to compute something on top of the graph without sharing the data, or with only allowing sharing the data with your local neighbors. So this is what we call public-private graph model, computation model. We have 2 papers in KDD and and like a follow-up paper that's on arXiv. So basically the model is, briefly speaking, basically like we have a private graph on top of each, like for each node, we have a private section of the graph that's only known to this user, but then we have like the public graph that's known to everyone. So for example, you can think about Facebook public relation graph. People have declared that you can share this data, like my network and so on, and then the part that people declare for themselves. So for the on-device model, the question is, can we keep all the private data and private contacts to user devices and basically compute machine learning problems on top of the whole graph? And that's what we achieve in this paper, and like now a follow-up paper. So like in that paper, we do K clustering and personalized recommendation and heavy hitters. And now in the new paper, we also do PCA and linear regression and so on and so forth. So yeah, like this is also to tell you more about the specific model on devices. I think I'm a little bit behind, so I'm going to skip this. Yeah, like the goal is to, yeah, the story is basically we only share like a sketching of the individual data that's also private to like the neighbors only, and like we can like do it because we only provide a sketch and so on. I guess like by that I want to conclude because I'm out of time. I told you about different privacy constraints that are becoming more and more important in analyzing machine learning and data mining tasks, in particular the deprecation of third-party cookies and maybe tracking IPs and so on. So this becomes like important. It results in many important practical and scalable techniques that are required to address this to get good privacy utility trade-off. We use clustering as a main tool, and there are many open problems in theory and practice, and many challenges remain. So if you're interested in these topics, I'm very happy to discuss. Thank you.
Now we are going to our next speaker. Let me check the program that we are on time. I think we are on time, or yes, we are absolutely on time. So the next speaker is Srini Devadas from MIT, as we in Germany say, Professor Srini Devadas from MIT. And I would like to take 1 minute to say something about Srini Devadas. So first of all, we need a individual talk or the whole talk to talk about his numerous awards. And I'm not going through all of them, but you just can check not only his webpage, but also I would say check his papers and from him and his group that were absolutely influential, not only in security, but also in computer-aided design. It is not that Srini is only interested in security aspects, but he's an inventor of POFs, and many of us, especially in our crossing project, know that this is an important, also really important innovation with a huge impact on many different disciplines, not only computer science, but also in particular in engineering. I myself with my group have worked in this area for a long time, and I was always hoping that one day I can meet with Srini Devadas, the great master. And at the end, I met him, and not only Srini Devadas has huge contributions to our community, but also in other communities like computer-aided design. He's also a very nice person. So I'm really happy that he's, because all the awards aside, there is other aspects that for me personally are very important, and you are a nice person, and I wish that everybody knows that. And I'm happy that he took his time, and he's going now to give his talk, and he's also heading an institute which considers machine learning and AI for a number of years before we had all these hype of around AI, and now he's going to give a talk about collaborative learning. Srini, the stage is yours.
Thanks, Ahmad. I hope you can hear me clearly.
Yes.
And thanks so much for the invitation. Obviously, we're all waiting for the pandemic to end, and so we can meet in person. But I guess eating chocolate, across multiple continents and enjoying each other's company is what we have here. So I'm paying for the chocolate from yesterday with this talk. So again, a real pleasure. Let me go ahead and share my screen.
Yes.
And just let me know if you can't see it. You should see a title that says Private Collaborative Learning with Data Transformation. And I also always tell people I'm going to be switching slides. There's not just the one slide in my talk. So if when I'm moving and if you don't see the slides changing, well, interrupt me, audio, what have you. So this has happened in the past. I guess Zoom bugs. But Ahmad, thanks for the kind introduction. I worked a long time in hardware security. I think Ahmad thought I was going to give a talk on hardware security. And then I said, well, I'm a little bit more excited, today or whenever it was that I responded on the most recent work we're doing on private learning using data transformations. And Ahmad said, you can talk about whatever you want. And I took him up on the offer. Vahab's talk was quite a nice setup. I'm actually going to talk about similar problems, but a different technique, as you will see, which I will detail over the next half hour or so. What does this talk about? I just switched slides. You should see my motivation slide. We want to outsource computation on private data. There's lots of data out there that has sensitive properties, medical data, financial data, etc. We'd love to be able to do really two things. We'd like to outsource the learning over the data, whether it's regression or something more sophisticated. We'd also like to pool together data and with people that we can't actually exchange data with because of legal reasons, for example, and try to exploit the fact that there's a lot of people out there with similar profiles, whether it's medical profiles or financial profiles, and get better models that can help with whatever problem that we want to improve, whether it's visual recognition or whether it's modeling economies or what have you. So there's really three dimensions that are associated with this outsourcing problem or this collaborative problem in my mind. Three major dimensions, right? There's the most important, really, as a security person, is you are going to create an algorithm and you're claiming it's private. What is the privacy guarantee? And it could be differential privacy, as Vahab just talked about. It could be something that's a computational guarantee, lattices, hard problems on lattices. Fully homomorphic encryption is a technique that allows you to do an encrypted computation using computational assumptions. And you have to essentially explain to people before you get any credibility what the privacy guarantee is. And it may be the case that it's ad hoc, in which case you got some issues with respect to selling it to the cybersecurity community, but doesn't mean it doesn't get used. And there's many varieties of that. So that's one dimension. The other dimension is there's usually a performance hit associated with the computational cost when you go ahead and do things in private. And again, fully homomorphic encryption is an example of this. Wonderful privacy properties, but really, from a standpoint of a practitioner, horrific overheads, like a billion times slower, and maybe it's 10 million now, but that's obviously something that isn't going to work, for example, for outsourcing deep learning and perhaps even inference. So that's the second part. And then the third part is what are you going to get in terms of the model that you get back, or the results that you get back on the computation after you've sent it over to the untrusted server and you get the results back? Is this utility cost significant? Is the fact that the accuracy of this model, if you added noise, for example, in a DP approach, your accuracy is going to drop. And we heard all about it. And sometimes there's clearly a trade-off here. Like you increase the noise, you get more privacy according to your DP definition, but your utility drops, right? So those are the three dimensions, and there's lots of approaches. This talk is not a survey talk. I want to tell you about things that are in the academic oven. Some of these ideas are not fully baked, but I want to tell you about them anyway. They're hopefully interesting to you. They're certainly interesting to me, but I'll just leave it at many different approaches, because you have these three dimensions, and one approach may be better in one dimension, but worse in the other two. And we'd love to obviously get a strong privacy guarantee, low computational overhead, and let's say perfect accuracy, same as what you would get in the with the original unencrypted data. We're not there yet. I'm certainly not there yet. Maybe there's going to be breakthroughs and we're going to get there, but I'd say as a community we're not quite there yet, and that's why this is still a research problem. I want to tell you again about a specific approach now that I've hopefully set the stage or given the context for this talk. We are going to take the data and we're going to do essentially, think of the entire data set. I'll explain exactly how this happens, and we're going to transform the data. And this transformation is going to have a privacy property that I'll actually talk about. It's an information theoretics privacy property. This is not adding noise to the data. It's actually a global transform over the data. And then this transformed data gets sent off to the server. The server is going to compute, whether it's regression or whether it's running a convolutional neural network learning algorithm, it's going to compute on this transformed data, and it's going to produce, let's say, a model for it, and it's going to send it back to us. And we're going to be able to use that model by applying for a new sample that we want to infer something about. We have a picture and we want to infer something about the picture, whether it's a cat or a dog. We would apply the same transform. So that transform is going to be private to us on that sample, and then we can query the model. The model is not going to be interesting if we don't apply the private transform to the sample. So this sounds a lot like fully homomorphic encryption, except the transform has nothing to do with FHE. And I'll show you what the transform is. It's actually fairly straightforward. I'd like to show you some results. I'd like to talk about how this can be extended to private collaborative learning. And so let's get started. So there's an equation here that I think should be familiar to most of you, but it's really not complicated. We want to do optimization. We want to solve some learning problem. There's a loss function. There's samples first. They're usually labeled samples, at least in our context here. X is the data, Y is the sample, X is a picture, Y, let's say the picture is of a cat. And we're trying to learn a model that minimizes generalization error. And we usually have a loss function. Maybe it's the L2 norm, maybe it's something else that we are trying to minimize, and we want to get this model F star. And so what happens here is we measure empirical error as opposed to generalization error, because generalization error is sort of this conceptual thing, and we need something numeric. And this is essentially what a host of machine learning techniques do. So the basic idea is that we're going to end up taking that, doing T of X. So the only change between the previous slide and this one is that we have T of X over here. So the labels stay the same, but I've taken the samples and I've applied a transform to it. And so T is going to be a private transform. And the observation, and this is not something that is particularly profound, and maybe these equations make things more confusing, but the intuition is that assume that you had this all-powerful learning method, and lots of strong assumptions here, but bear with me. You had this all-powerful learning method, and you had a transform that was bijective. And so you can also consider it to be invertible. So you can go both ways in the transform. And if our optimization problem has a unique optimum, then you're essentially saying that if you apply any bijective transform and you found that unique optimum using this all-powerful learning method, then when you get the model back, this model that's FT, because you're now running over a different data set. So the model that you wanted was F star, but now what you get is FT star. Well, you can essentially get F star from FT star by applying this little composition that essentially says I'm going to apply the inverse transform, right? So you can take the model and you can do the inverse transform of it. Or as I mentioned before, you can just take the FT star model, and every time you want to use it for a new sample, you can apply T to that new thing. So you got T and you got T star, and this allows you to go both ways. Hopefully that was at least intuitively clear. Now the question is, what does this get you? Well, what this gets you is that we're saying that we do not want to do an operation by operation equivalence like we do in encrypted computation approaches like FHE. We're doing this arbitrary bijection transform. I'm going to give you examples of that. We're assuming that an equivalent optimal model exists, and we really don't need to make that assumption. Something that's close to optimal in this transform space is really enough for us, because whether we get 99% accuracy or 98.99% accuracy, I mean, who can tell whether one model is actually better than the other or not for a different test set, right? So we would like to get something that has pretty high utility, and as long as that approximately equivalent optimal model exists, given this transform in this transform space, we're going to be pretty happy. And now you can view T as a key and T of X as this sort of quote unquote encryption procedure. But it's a much weaker encryption procedure than what the cryptographers use in FHE, for example. So I'll be upfront about that. But the question is, what is the security property of this encryption procedure? And we'll certainly talk about that. So the overall picture looks like this. I mean, we have a name for this framework that I'll let you read. But as I said before, and this is a little bit of a repeat, but hopefully this will become clear seeing this picture as to what the overall operational flow of our techniques are. So we got the user on one side who has private data, got the server on the other side that is untrusted. We're going to do maybe some data pre-processing that I'll talk about a little bit later, but you could be augmenting your data set, etc. No problems there. We're going to apply a uniform transform on the data. And you can think of this as multiplying it by a random matrix, one layer neural network or something more complicated. Doesn't have to be a linear transform. It could be nonlinear, but we have to be careful here that we'd like this transform to be invertible. And so sometimes if you add too much nonlinearity, you lose invertibility. Because as I said, we want this transform to be bijective, so we get eventual utility for our model. So now we dump this data over to the server. We obviously have to talk about what the server can learn from this transform data. I'm going to spend several minutes on that, but we'll get to that. The server is going to train on this transform data, produce a model, which we're calling F here, and then send the trained model back. And as I've said to you a couple of times already, you can now use this model only with your uniform transform, because this model won't make sense on non-transform data. So for inference, once you get the model back, there are a couple of ways you could do this. You could compose the model with your transform, as I show here in model reconstruction, or you can say every time I have X new, which is a new sample, I'm going to run this private transform on it, and then I'm going to ask the model, hey, what's f of t, fx new, right? So that's the setup. Definitely reminiscent of encrypted computation approaches, but the privacy guarantees and what you get in terms of utility are a bit different. So what is this transform? Well, this transform is extremely straightforward. It essentially says, you know what, let's say I have an image that is square root of d times square root of d. So it's 100 by 100 in terms of the square root of d is 100. Well, let's pretend that it turns into a row vector. Obviously, there's going to be d elements in the row vector. And so that's what you see here. It's 1 times d. The transform is a d times d random matrix that can have 0, 1, or -1 elements in it. Right? So what we're going to take this particular image, we're calling it x1, and this dog image I'm calling x2. And if my data set has 2 images in it, I'm going to multiply both of those images by w, which is this random matrix. That's why this is a uniform transform. It's being applied uniformly over all the data samples. And so now x1 times w, if you think about it, you have a 1 times d row vector, you're multiplying it by a d times d matrix, you're going to get a 1 times d row vector, which is your transformed vector. And because w is a random matrix, and this is a fairly, obviously global transform, you're essentially going to get gobbledygook at the other side of it that corresponds to these pictures. And these are not to scale, and these are not the correct pictures. They're just hopefully evocative. So that's the transform. That's our random linear transform. So now our job is, what is the privacy guarantee you're going to get if I expose a lot of samples all multiplied by this random matrix W that is going to be secret to the adversary? What is the privacy guarantee that you get? And the other part of it, which is empirically going to be empirically answered, is this transform data. I'm going to go off and learn on it. What is the utility that I get? And remember, if I now have a new image, and after I get my model back, I'm going to multiply that image by W, exactly like I said here, and then try to recognize that image using this model as a cat or a dog or an elephant or what have you. Right? So that's the setup, and hopefully all of that was clear. So the entire set of data samples is going to be multiplied by W, and so there's no expansion in the data set in terms of the size of the data set. So that's good news. So n times d data set, if I had n samples, and then n times d transform data set, that's what I get at the end of it. Obviously, this x.w is exposed to the server, but I'm assuming that my data set is private and my w is private as well. There is clearly a chosen plaintext attack. So if you ever got into a situation where the adversary knows your private data already, or you take public data that is known to the adversary and you multiply it by w and expose x times w to the adversary, and if you do that for enough samples, in fact, if you do that for d samples, then the adversary is going to simply solve a linear system of equations and discover your private transform given knowledge of your input data, right? But the whole point of this is outsourced learning, because you have a private data that you do not want to expose to the adversary, to be clear. So we're assuming here, and this is I want to say this up front, that there is some entropy in this private data that you have, and the adversary does not know all of your private data. It may, obviously, the adversary could have partial information, that's okay, but the adversary does not have complete information of your private data X Otherwise, the game is lost already. I mean, we're not even in the game, right? So all the information theoretic security properties that we're going to be able to show here, or the primary one that we're going to show, is that there's some entropy in X. And if you have some entropy in X and W is randomly selected, then there's a privacy property that says that the adversary is not going to be able to discover a lot more about your private data. I'll formalize that, but there is a privacy property there. Good. And so how do we formalize this? The question we want to answer is, you're given an observation, which is this transformed data. There's obviously some entropy associated with the private data. How much information can an adversary recover that the adversary did not know when it sees an observation and it sees a second observation? It sees a whole bunch of transformed samples that are in this X times W that we have here. And so we're going to use probably approximately correct inference theory, or it's a pack theory, to explain this. And we're essentially saying, can adversary approximate with error smaller than epsilon the input with confidence at least 1 minus delta? So these are epsilon and delta, which are used in very different ways from differential privacy, which also has epsilon and delta. So let me be clear here that symbols, of course, are overloaded, especially across different technical concepts, and this is no different. Epsilon is the approximation error. So if epsilon is 0, then that means that you end up with exactly the private sample. You've discovered that with no error. And if delta is 0, then you've discovered it with 100% confidence. So what you want here, from a security standpoint, you want epsilon to be large and delta to be large as well. So the adversary has low confidence, even in approximating in a very rough way, in a loose way, right? So the reverse of differential privacy, I want to make that clear, right? But hopefully this is not too complicated. There's essentially a definition that is associated with what I just basically told you, which is that you think of a mechanism, and this mechanism in our case is this private transform that we are simply going to use random matrices and multiply the data samples. And we want to say that this private transform is resistant to pack inference. And this definition essentially says, well, you can read this, but there does not exist a possibly randomized algorithm such that the adversary with high confidence, small delta, can closely approximate with low epsilon your input data, and therefore basically break the scheme, because it doesn't matter that you use this random matrix, given enough observations, even though you have entropy in your private data, your adversary is going to be able to approximate this, right? So obviously, this is just a definition. In order to prove a theorem, we need some assumptions, and there's going to be some assumptions associated with the data distribution. Obviously, the adversary, there's low entropy, and the adversary has a lot of prior knowledge. Your epsilon and delta aren't going to be that great. Your epsilon is going to be small, your delta is going to be small. But if there's a lot more entropy, it makes sense that epsilon is going to be large, and delta is going to be large as well, which means that you have greater security. So there's a parameterization here, which is quite different from DP, but there is a parameterization. So I'm not going to spend a lot of time on proofs and things like that, but I do want to give you some sense of how we did this. You are basically in a fairly simple, straightforward situation where you make some assumption about the input distribution of your samples, and then you say, I have M samples that I'm exposing the transformed samples of. So you had M private samples, you're exposing those M transformed samples, and then using a mutual information argument, you can get a lower bound on the sample complexity for an unbounded adversary. right? So this is not a computational security argument. It's an information theoretic argument that says, you know, if you have this much entropy in your private data, you can expose a million transform samples, and you can now, you know, show a theorem that for particular epsilon and delta, an adversary cannot recover with that particular epsilon and delta, cannot recover your private samples within epsilon and with confidence 1 minus delta. That's again intuition. The details obviously are not going to be covered here, but we do have a paper, and I'm happy to point people to that. So the main result is that we have is let's assume that W is selected to be a 0, +1, -1 random matrix, and we have many results, and maybe this is not the main one at this point, but one of the simpler results to state is, let's assume that the prior knowledge that the adversary has of your of the private samples is that it's a Gaussian distribution with some variance tau. Now our mechanism T satisfies epsilon delta pack security if m is less than or equal to, you know, c times d, where d is the dimension that we had, and c is a function, a fairly complicated function that I won't foist on you, of epsilon delta and tau. And so just as an example, I told you that, you know, if you had 0 entropy, then D samples are going to completely break the scheme because you do a chosen plain text attack. Well, if you had some entropy corresponding to this tau that you have here, which is usually a function of the dimensions, then you have a, you know, fairly strong scheme that says even if you expose a number of samples that's 30 times the dimension, right? So if you had an image that was 100 by 100, and, you know, the dimension would be 1,000,000, and if you expose 30 million transformed images, then you know, if you assumed a particular tau, as I said here, it's going to be hard even for a computationally unbounded adversary to discover the private samples that you have, because there's enough entropy in those private samples, right? And so this is just a parameter to give you a sense of what I'm talking about, because obviously equations can get pretty hairy pretty quickly. And I'd reiterate that you're assuming that you have entropy in the data, so there's a factor here of in this case 31.5 with respect to the samples that you need as an adversary to do this break or inversion. And so suppose you did not have a lot of entropy in your data, or you wanted to use public samples in order to do the learning. So now you're worried about this because, you know, if you start exposing public samples and this adversary knows public samples and can see the transformed public sample, they can easily get W from it if they see D samples. Well, so there's this nice thing that you could do called mix-up, which is not something that we thought about, but it's been out there in the data augmentation world and used in many different contexts, which says that you can take your, you can add your private data to public data, and then you can do this and augment your data set and get these get new data elements that have a little bit of entropy in them. If in our context, if for example one of the images is not public, right? So in the mix-up was proposed in a sort of a non-private context, and it's just what you see here. You know, let's take a couple of images. Let's take 70% of one image and 30% of the other, and then create this image that you see on the right. And you label it 0.7 and 0.3. So now the label is not this one hot vector, but it's reals. The way we're going to use mix-up is we're going to be able to use public samples and keep lambda, which is this factor, hidden. I mean, it could be 0.7, it could be 0.6, it could be whatever. I mean, that's not essential to the scheme, but let's assume we do that, and we mix in and add entropy, if you will, to public samples corresponding to our private samples. So even if we only had a small number of private samples and a lot of public samples, and you want to use public samples to do learning and optimization, you could use mix-up for that. So that's all I wanted to say. So we don't need to get too hung up on the fact that we want to use public samples. You can always add entropy to that. So so the algorithm, as I mentioned, it's really pretty straightforward. All we did was potentially use mix-up and and multiply this this data set with a d times d random matrix. And so so here's what happens if we try to do transformed handwriting recognition or on the MNIST data set, right? So this is just a very preliminary results. So the MNIST data set has 60,000 samples in it. You can get fantastic accuracy with fully connected networks. This is a trivial data set, honestly. And so it's considered one of the easiest data sets, maybe the easiest data set that's out there. So obviously we'll start with that, but hopefully we won't end with that. Now, if you do mix up, you can get effectively the same thing. I'm just putting this out as mix up doesn't hurt things too much. In some cases, it can improve things very slightly, like you go from 98.5 to 98.6. Notice that you can now increase the number of samples. Mix up is the data augmentation approach. You can go from 60,000 samples to 180,000 samples, right? So now let's say that we now take these mixed samples, and to be clear here, what the adversary is going to see is not this thing that looks like a cat, obviously. So this is completely exposed. But remember that adversary is going to see this mixed up image that has some entropy in it if the adversary doesn't know about the dog image, multiplied by W, right? So then it's going to look like gobbledygook. And that is what we're calling two mixed transform training. So now there's been a dramatic change in the data set because we multiplied it by W. And it takes a little bit longer to get the same model back. And you get basically the same accuracy. Maybe if you've lost 0.1%, which is noise. So this basically says, hey, utility seems kind of reasonable, at least for this trivial data set. If you believe the security property, and that essentially says, you know what, in this particular case, you would have to expose 1 million transformed samples to the adversary for the adversary to have a chance of recovering your data, provided some of these MNIST samples are private to the adversary. Obviously, MNIST is a public data set, and so operationally that won't work. But if you had your own handwriting to recognize, and this whole thing was about protecting your private data, right? So assume that half of MNIST is private, then you have enough entropy to run this process and get a privacy guarantee out of it. So what happens when? Let me go back. If you do things that are more interesting, what happens if you want to use CNNs, for example? Well, as I described to you, the technique doesn't work. I mean, it fails miserably from a utility standpoint. It would work exactly the same from a privacy standpoint, but it doesn't work from a utility standpoint because convolutions are local computations, and we've done this dramatic transformation of the data by multiplying it by this matrix. But we can tailor this transform to CNNs. So what we can do is, rather than multiplying by a single matrix, we can multiply by many different matrices by essentially doing a pretend convolution. So what I'm showing here, again, just take the basic idea from this. Imagine that you have a 3x3 k equals 3 filter. You're convolving this image, which is square root of d times square root of d, and your stride is t, which you can assume to be 1, and you're walking through this image, essentially doing the convolution. And this is obviously ubiquitous in machine learning. And you think of the actual data elements that you're looking at as a 1 times k square row vector. So it's k times k, and so you get 1 times k square row vector, and look at that row vector and multiply it by a k square by k square random matrix. So there's going to be a whole bunch of different random matrices that are each k square by k square that are going to transform our input data corresponding to, let's say, an image, and produce this transform data set. And so if your stride is t and your dimension is d, your dimension is d, and each of the images has a length and width square root of d, then if your convolutional filter is k, then you're going to go left to right q times, you're going to go top to bottom q times, and you have q square of these matrices, which are each, by the way, the W matrices are each k square by k square, right? So hopefully, that was kind of somewhat understandable. This picture hopefully makes things a little bit clearer. But we're going to transform our data set by multiplying with many different random matrices. And then we're going to take our CNN and we're going to add a layer to it in front of it. So whatever CNN you use, add a layer to it that corresponds to a whole bunch of learnable matrices whose weights you do not know. And so this is on the server side. The server gets transformed data. You get these, you add these learnable matrices to the input of the server corresponding to these k-square by k-square individual fully connected, you can think of them as fully connected layers. And then you have the rest of the CNN that corresponds to the convolution, which is a standard thing, right? So that's our transformation. And if you do that, then things work a lot better, right? So same privacy property, nothing different because you're still multiplying by random matrices. It's just that these random matrices there are many of them and they're smaller. Each of them is smaller. And I won't bore you with going over all these numbers, but the bottom line is you have some utility loss, but the transformed data set, it doesn't run much slower than learning on transformed data is not that much slower, as you can see from the CPU times, and you get pretty close, right? So you're doing a very global transform, but you're still at an 89.8, for this transformed data when you're learning on ResNet, versus 93.2. And you say maybe 3% is large. I say 3% is small. We can argue about that, but these are preliminary results, and I just want to give you a sense of where things are at. Right. So let me finish up here, just sort of giving you some sense of how we could pull off collaborative learning in this framework. So one of the things I'm excited about is there's an easy extension to this approach that allows you to get to, I would say, a fairly lightweight computation collaboration scheme where you don't have to trust other parties. So Ahmad and I, we like each other, but he's in Europe, I'm here. I got some hospital data, he's got some hospital data. We just mandated to not be able to exchange data, but we'd like to be able to pool our data sets and get a model back. And federated learning is one example where you can do things like that. But here's an approach that's quite different from federated learning that uses this transformation-based approach and also doesn't use these heavyweight computation techniques like MPC, which are fairly slow. They're like maybe not as slow as FHE, but they can get pretty slow. So one way is to say Ahmad and I, decide on a transformation matrix. But if he knows the transformation matrix and I know the transformation matrix, I can look at his transform samples and I know the transformation matrix, so I can actually get his samples and vice versa. So there's really no privacy there. And so then you say, well, okay, maybe neither of us knows the transformation matrix and we use MPC to create the transform samples. Well, that's going to take a long time. So that's not so great. Now, if he uses an independent transform matrix, I use an independent transform matrix. Neither of us has any idea of the W1 that Ahmad used and the W2 that I used. Well, then you're taking images that essentially roughly come from the same distribution. Perhaps they're lung scans, and then you're multiplying it by in two random ways, and you're trying to get some learning engine to learn on this, and there's no chance, right? This doesn't work, right? So here's how you could solve that problem by keeping things independent across Ahmad and me, which is we're going to take our data sets and we're going to transform them independently, but we're going to solve a different learning problem that we call task augmentation, right? So owner one is Ahmad, he's got a data set. Owner two is me, I got my data set, right? We can't put these data sets together. But someone can obviously create this composite task that corresponds to taking one of Ahmad's images, one of my images, putting them together side by side, and taking Ahmad's label and my label and putting them side by side. So you got Ahmad cat, Srini cat, and in terms of the images, and the labels are what I just said, right? So so far we don't have any privacy yet, but I'm just telling you what this composite task looks like. And essentially what happens here is I can now train a model on this composite task. So let's not worry about privacy for just a minute. And I can train a model on this composite task. And in order to run inference, I need to give this model some composite data sample. And I could take a new sample from me, and Ahmad could take a sample X new, X1 new, and add one of my samples to it, and query this model and get something back in terms of the label. And he's only interested, it's going to give you two labels back. He's only interested in the first label. And he could do this and do majority voting because he can take his one X new sample and essentially do majority voting based on the labels he gets back. So the key idea, and this is the last idea that I promise, is this entire setup that I just showed you on task augmentation does not require exposure of samples if Ahmad uses T1 to transform his samples, and I use T2 to transform my samples, send them over to the server. The server does the task augmentation and the random grouping, and then creates the model. And so that is the key. T1 and T2 are independently chosen and are secret to each other. I'm going to get this model F. And then, as I said before, in order to do private inference, Ahmad is going to get the model back. I'm going to get the model back. I don't need to know T2. Excuse me. I know T2 because I'm the second person. I don't need to know T1. And so down at the bottom here, I can take one of Ahmad's transform samples and then take my new sample and transform it because I know my own transform and use it to do inference. All right. So that probably went a little too quickly, but happy to answer questions since I'm basically done here. Each owner can independently run inference using the transform samples of the other without knowing the other's transformation, the T1 or the T2, as the case may be. And so this works pretty well as well. I mean, again, with the proviso that these are preliminary results, and you can actually get a little bit better than aggregating in a non-private way the samples by the aggregation in the private way can do a little bit better than individually not sharing at all. But aggregating in a private way is not quite at the level of non-private aggregation, right? So if you look at non-private aggregation, you can get, as I showed you, 93%, from before. And if you do this private collaboration, you're a few percent worse. But you are doing 87.8 is better than, for example, what do I have here? ResNet 56, 86.1, which is the individual things that each person would get. So you improve things through aggregation. So the summary is, I tried to give you a feeling for this very preliminary approach on transformation-based learning that does not assume an operation by operation equivalence of the encrypted world and the plain text world like FHE does, but essentially says, I want to do the one-time transform and I want to go off and allow the server to go compute on this. And I want to get back something from the server that corresponds to something I could use, a usable model that hopefully is going to be something that's pretty close to the optimal non-private model. There's a chance here that these approaches would be significantly more efficient. And we have a lot of work to do with respect to showing utility and showing privacy properties to card-carrying cryptographers. And I certainly welcome questions and criticism. So let me go ahead and stop sharing my screen here so I can see people and see if there are any questions.
Our next honorable speaker is Rebello. He joined DARPA some years ago, I think around 2018. He served as a technical director for emerging technology and technical lead for emerging threats in the Office of the Undersecretary of Defense for Intelligence. And Keith has also lots of activities regarding material research, but also hardware focused research, which is, as I mentioned this morning, is fundamental. And I also pointed out to his talk that we are grateful to have him. He's a program manager in DARPA, and whoever of you has the opportunity to talk to some of DARPA managers and be part of the DARPA projects. DARPA projects are in general, I personally think, from my point of view, very innovative. And DARPA managers, most of them that I talk to them, they really know what they're talking about. And this is why I always invite them, because I personally learn new things, and I hope that this is the same with you. He is doing very exciting programs, and he's going to give us some insights today for hardware at the heart of the system security, threats, and opportunities. Keith, thanks a lot for being here, and please, the stage is yours.
Thank you. Thank you very much, Ahmad. This is my first crossing, so I'm very excited to be here. Again, I wish it was in person and I could talk with you at sidebars and coffee and dinner and all that good stuff. But please feel free to ask questions, and don't hesitate to reach out to me afterwards if you have other things that come to mind that you'd like to chat about. We have really been at this for a while. We've traditionally been focused on higher levels of the system stack, right? We've been analyzing vulnerabilities in applications, in our operating system. Apologies, someone is calling. There we go. In our operating system. But one of the trends that we see at DARPA is that our adversaries, are the bad actors of this world, they are moving down, further down into the stack, into firmware, into hardware. And what I want to talk with you about today are some specific security threats that we see, some opportunities in the hardware space, and then what we at DARPA are doing about it. So let's talk about threats. There's many different types of hardware threats. Some that are unintentional, like implementation flaws, side channel leakage types of things. Some require direct access, where adversaries have access to the hardware and then do malicious things. But regardless of any of these types of attacks, I think the important thing to note here is they're serious, right? We care a great deal about them. They can lead to complete system compromise. And the kind of class of attacks that I want to focus on today are all the way down at the bottom of this slide, are the supply chain types of attacks. So I wanted to just kind of impress upon you the complexity of this problem, of the supply chain problem. And so this slide here just shows kind of the high level magnitude of the problem that we're facing. So this slide illustrates the kind of lifetime or the travels of a component that is part of the F-35 fighter, the Joint Strike Fighter. And, when I first started digging into this problem, I was shocked at, how these things move around. So this one part has moved all around the world multiple times, bouncing, back and forth, and has changed hands about 15 different times. And so, that makes this a very, very challenging problem. And to kind of foot stomp on that, this slide here I borrowed from Bunny. Bunny Wang gave a really good talk a couple of years ago at Blue Hat in Israel, and he put on kind of his black hat, if you will. If he was an adversary for a day, what would he do to disrupt the supply chain? And you can see from this this picture here, kind of where his thoughts are. in terms of the purple side of things. But there are many different pain points here on this slide. So if you control the supply chain, you could insert malicious activity way on the left here of the slide when you're actually making things, and all the way through the supply chain to swapping out packages when they actually get delivered at their end. So there are so many different pain points here that it really makes the problem challenging. And we know that these types of things are happening. So there was an article that came out a couple of years back, October of 2019. Actually, this is the article that got me started down this path. You might have read it. It was called the Big Hack from Bloomberg Business Week. And in this article, they had postulated that supply chain implants, hardware Trojans, were found in the server motherboards. These server motherboards ended up in data centers of very large companies, hyperscalers that we all are well familiar with. While these reports were never confirmed, we at DARPA believe that these types of attacks are possible, and this is something that we need to worry about and develop technologies to mitigate. So if the supply chain problems that I kind of mentioned before weren't challenging enough, when we start talking about Trojans, things get even more challenging. So this is a taxonomy of Trojans, and you can see that it's really vast and quite varied. On the left, there's many different places where these Trojans can be inserted, and then the Trojan behaviors themselves are quite varied and can be quite complicated. There are many different triggering mechanisms that a Trojan can employ. There are many different effects that a Trojan can cause. And, again, there's many different signatures that a Trojan can have. And so, that also makes this problem very challenging. To make it, even harder, what this slide shows is two SSDs. So these are identical part numbers from a manufacturer, but you can immediately notice that the main components on these SSDs are different, right? So the actual SSD controller chip is different. The NAND flash memory is different. The RAM is different. So, determining whether or not something is just a benign kind of change, or if it's malicious, can be very challenging, especially, in this day and age of COVID, where we have a lot of supply chain sourcing issues and challenges, and manufacturers are having to swap, different components in. This can be a very challenging problem. And in this case, this is a fairly simple case where there's, a fairly simple device where there's only a handful of components, right? But as we start going to more complicated systems like this server motherboard here on the left, where we have thousands, right, of different components on the board. In this particular example, you can see we have two CPUs, right? And so each of those CPUs has multiple cores in it, and those cores can each nowadays execute multiple threads. And then in addition to those computational units on that board, we have a variety of other components, right? We have a GPU, we have different controllers, we have a memory IO controller, disk IO controller, we have a baseboard management controllers, we have TPUs, we have network interfaces, there's a lot of different, components on there that have compute built in. And then since this is a server, right, we might actually be running multiple virtual machines on this hardware. And each of those virtual machines might be running a server grade operating system. And that operating system might have, 1,000 different processes running. And so, you can see how this complexity starts to snowball. And that's just one system, right? And then we talk about, in the middle here of inserting these into maybe a rack, right? So we have 10, 20, 30, 40, 50 servers in a rack. And then that goes into a data center where we have maybe 1,000 different systems. So, the question really that I had was, is it even possible to detect, this little hardware Trojan, right? In the Big Hat article, you saw there was that little filter capacitor that was switched out, and instead of being a passive component was an active component. Can we detect something like that in this vast sea of complexity? And so I started a program called Safeguards Against Hidden Effects and Anomalous Trojans in Hardware Sheath to answer that question. And it was really kind of designed to be a short-term 18-month effort to go after some really, high-risk research to look and see if it was possible, to answer that question. Can we find Trojans in this very complex environment? One of the challenges we have is that, there aren't a lot of examples of these Trojans out there in the wild. So as part of this program, the performers were tasked to build a representative Trojan that they would then insert into representative hardware that we care about. So in DoD, we care about things like, servers and high-end network routers, which you can see on the right here. And so we had a number of performers. There was a number of different approaches that people took to try and address this challenge. They had developed isolation techniques to try and cut through this complexity and all the noise sources that we were talking about. Techniques to amplify Trojan signatures, and then using machine learning techniques to try and sift through that vast sea of complexity to pick out the needle in the haystack. And so we developed a number of different Trojans, exemplar Trojans on the program, a variety of different man-in-the-middle attack types of Trojans. So we had TPM, so trusted platform modules, rogue trusted platform modules, rogue baseboard management controllers, malicious Ethernet and USB devices. We developed a malicious NIC, so a network interface card that had the ability to access main memory, so direct memory access over PCIe into things that it probably shouldn't have been able to access. And then also malicious machine learning accelerators, so FPGA-based deep neural network machine learning accelerators. And then we had a number of different approaches that were successful in detecting these types of attacks. So the first one I wanted to talk about is an RF side channel technique. Here they're looking at second order effects, electromagnetic effects from components. And so this one was really focused on detecting these FPGA accelerator Trojans. So in this case, they had developed a Trojan that would classify aircraft. So it was able to detect and tell the difference between military aircraft and commercial jet airliners, for instance. And what the Trojan did was it modified that algorithm to misclassify a particular country's military aircraft and turn them into essentially passenger planes. And it was just a very, very slight tweak in the last layer of that neural network. And what this technique here was able to do was detect even these really small changes to the FPGA routing and determine whether or not the Trojan existed in the system or not. And so what they did was they trained on kind of the RF signature, if you will, of a good known system behavior, and then they were able to detect, differences and changes in that behavior. But this turned out to be a very powerful technique, which allowed us to even detect Trojans that were dormant, that hadn't been triggered, weren't even active. So very, very interesting research. Another technique that was very successful was this idea of distortions, taking a system and putting it into a state that it normally wouldn't exhibit in order to try and elicit Trojan behavior and kind of trick the Trojan into revealing itself. And the challenge here was, how can you distort the system in a way that you don't disrupt the system or cause the system to crash or take the system down. And so, this performer was able to show really, really great success in detecting man-in-the-middle types of attacks by looking at signatures and behavior. It turns out that the Trojans oftentimes have a different response than the base system when you expose the Trojans to different effects that they normally wouldn't see, that they didn't anticipate in mimicking. And so this turned out to be a very effective technique to detect man-in-the-middle attacks. Another thing that we investigated and looked at was the idea of building a model of the system. So here the hypothesis was, can we create a model of the power delivery network of a system and use that to detect changes in the system? And so what we did here was just with a few points. So just by measuring, 3 or 4 points on the board, we were able to, and knowing some information about the design of the board, we were able to build a model of the board of the power delivery network. And it turns out that when you have Trojan behavior and different functionality than what the system was originally designed for, that manifests itself in power draw and the power delivery network. And so we can actually detect if a component that shouldn't be there was substituted in. We can detect malicious behavior and malicious components by examining differences from kind of a golden or reference model. And so this showed some really promising research that gives us hope that we can try and find these things in these very complicated systems that we aim to protect. But there's still a lot of unsolved problems here in this space. So we still have a problem of noise, right? Even in this RF technique, we have to be very careful because, as I said before, we have thousands of, components on these systems. And so, there are a lot of noise sources. You have to be very careful in how you isolate signals and components from each other. There are an incredible number of variations, and these variations are only growing due to the supply chain concerns that we've had. And so we need techniques that help us figure out if components are benign or malicious. And then these systems can often run lots of different workloads, and we need systems that can tell whether or not these workloads are malicious or not. All of the techniques that I talked about really rely on the ability to have a reference or a golden sample. And oftentimes, it's not guaranteed that we will be able to have one of those. Then in that SSD example that I gave, right, even if we buy an SSD and use that as our golden sample or reference, the manufacturer, they could have 5 other versions of that SSD that, are the same model, but have different components in them. So it's not always possible to have this golden reference. And then, finally, we don't know the provenance of everything in our systems. And today, really, we tend to trust the hardware that's in our systems, and that is something that I think we need to be a lot smarter about and really start adopting what people refer to as a zero trust model, where we don't just implicitly start trusting all of the system hardware. So let's start talking about some of the opportunities we see in this space. There are hardware-based protections. So, there are actually, we have a lot of tools in our toolbox, right? We have security features that have been integrated into our processors, right? We have things called memory management units, right, which control memory access. We have control flow integrity being integrated into processors these days. There is memory tagging. We have hardware-based isolation, right? We have, in addition to virtual machines and the like, we have stronger jails. We have Trust Zone and SGX, and we have IOMMUs. There are roots of trust, hardware roots of trust. We have trusted platform modules. But one area I think where there's an opportunity is in the overall security architecture. And that is something that we have really been focused on at DARPA, is trying to take all of these tools in our toolbox and build systems that help protect us against these threats, right? And the reason why we need to do this is because our current state-of-the-art practice, which is software patching, we know that simply doesn't work, right? Here we have a plot of data from Mandiant FireEye. So they took data from, I think it was 2018 to 2019, and they looked at the time for, I think, 60 different exploits, the time for which, from which a patch was released to when that exploit was detected in the wild, right? And so on the right of this plot, we have our 0-day exploits, right? These are things were being exploited before patches were even created. But what is kind of shocking and disturbing is kind of the stuff here on the left, where we see even after patches have been deployed, even sometimes after many, many years, systems are still vulnerable because, for a variety of different reasons, people don't upgrade and patch their systems, and these systems are vulnerable. And so we know that this shows that evidence that patching simply doesn't work, and so we need a better way, right? I mentioned before that we see our adversaries, moving down the stack into the hardware, into the firmware, and this is just evidence of this happening. Microsoft and Google have both come out to say that 70% of the security updates that they've been doing are related to memory safety errors, so buffer errors, and so these are things that are weaknesses due to hardware flaws, and so we know that our adversaries, bad actors, they are running rampant. Most of the cyber attacks that we see today are actually exploiting these types of hardware weaknesses. And so I have a program called SITH, which stands for System Security Integration through Hardware and Firmware. And what this program seeks to do is really flip the script and change the paradigm, right? So we were talking about how we're always putting these software patches, these band-aids, right, up at the, you know, the top layer of this stack here to protect us. But you know, there's always another route to the weakness, right? There's always another way, maybe in that same program or maybe in a different program, to find a way to get access to that weakness down in the hardware and cause a vulnerability and exploit. And so what we seek to do on SIT is really simply build better hardware, right? It's to address the problem at its root down in the hardware. And so the goals of the program really were to close entire categories of these weaknesses. So we took the CWE database, so the Common Weakness Enumeration database that MITRE has created, and we kind of isolated the weaknesses that focused on hardware, and then we chunked those up into 7 large categories, which you can see in this pie chart here on the right. Things like buffer errors and injection attacks and information leakage attacks, and you know, you can read about those. But the real goal of the program, because nobody wants to pay for security, right? That is one of the reasons why we haven't really seen security been widely adopted to date, is that it's always a cost that no one wants to pay. And so the goal for SIT was to try and create these security protections with minimal cost impact. So minimal impact to performance, to power, to area. And we wanted these architectures and these techniques to scale, right? We didn't want to develop one-trick ponies or one-shot protection mechanisms. We wanted to develop techniques that would scale not only across different classes of CPUs, but across different architectures as well. And so on the program, we primarily focused on the RISC-V ISA. So this was an instruction set architecture that, you know, is open, and we could freely modify and change to our heart's content without having to, you know, pay expensive licensing fees to this company or that company. And we focused on 3 different classes of processor. 32-bit microcontrollers with no MMU, so things that, you know, you might find in an IoT device like your toaster, to, you know, 64-bit CPUs that run, you know, modern operating systems like Linux or FreeBSD, to very high performance, out of order superscalar 64-bit CPU type processors that you might find in a high performance computing environment. So, you know, I wanted to illustrate how some of this technology works. So this is a simple, you know, program that just, you know, takes, it has 2 strings. It asks the user for input for a single string, and then it just prints out the results of the 2 strings. So very, very simple program, but I think it's a good way to illustrate how some of the technologies that we built on the program actually work. So, you know, how does it work as intended, right? So here in this example, we have a user, and they are inputting in a string ABC, right? And so ABC then gets stored into A, and you can see that down here at the bottom, right? So you have ABC, the first 3 bytes of the array A gets stored, and then you have your carriage return, and that goes into A, and then B is, you know, just what B was created as, which was string 2. Now, if an adversary wants to exploit this piece of code, here we have a simple buffer overflow attack, right? So instead of typing in ABC, now we do A, B, C, D, E, F, G, H, I, J, K, L, right? So we have this much longer string, a string that is larger than what we defined A to be. And so in this case, the computer, again, is dumb. It'll just do what you tell it to do. And so it will happily, overwrite A and load A through L into memory. And in this case, it would overwrite the portion of B. So instead of now string 2 being printed out, we have IJKL being printed out. So your classic kind of buffer overflow. So the first technology that I want to talk to you about today is called Sherry. So this is our capability hardware enhanced risk instruction architecture. And what we've done here is replace pointers with what we call capabilities. So you can think of these as kind of pointers on steroids, or fat pointers with metadata. You can see an example of what a Cherry capability is on the right? So here we add additional metadata. In this case, we have permissions. So we can make a pointer have read access or write access or execute access. We can have it be cognizant of the bounds of memory that it's allowed to access. And with this, we can do many interesting things. We can have very strong memory protections, both temporal and spatial memory protections. We can have very fine-grained control of memory and do very fine-grained compartmentalization. We can extend memory protections to other parts of the system, like accelerators and microcontrollers and DMA engines and the like. But to do this and deal with these new capabilities, we have to make some changes to the hardware. We have to have new instructions that know how to deal with capabilities, and we have to have software infrastructure that is aware of these capabilities. So our compilers, our operating systems have to be aware. But if we're able to have those types of components in our system, then we can protect against these types of attacks. So if we go back now to that simple example program, how is a buffer overflow mitigated with Cherry? Right. So here, when we create A and B to begin with, instead of pointers, A and B now are capabilities. So the capability knows that A is 8 bytes and B is 8 bytes by definition. When that memory is allocated, that capability is known to be 8 bytes. So in this case, when the program is executing, when the instruction tries to go beyond the 8th byte, like when the 9th byte, the S is tried to be written to memory, the processor actually will stop and throw an exception because it knows that A is only supposed to be 8 bytes long, and someone is trying to write beyond the bounds of that array. And so then it's up to the operating system to decide how it wants to react to that exception. But in this case, it would stop the letter S from being written to memory, and only A through H would be printed out. And then of course, string 2 would be printed out. The other architecture I wanted to talk with you about is our hard architecture. So hard is our hardware architecture resilience by design. It takes a very different approach than Cherry did. So here, what hard is trying to do is sense the context of instructions that are being executed by the processor and try and determine whether or not those instructions are benign or are they malicious. And their implementation has many advantages. So one, they're not changing the main processor pipeline. They are using parallel kind of security pipelines shown in green here, which just pick off information from that main pipeline to make decisions about the behavior. And so the main pipeline is not changed at all. And in this case, that means that there's no impact to performance of the system, right? The pipeline executes just as normal. So that's a huge benefit. Another big benefit is because they're not changing that pipeline, they're not, needing any new additional instructions. And so this architecture works with legacy code. And so there's no need to recompile your software to take advantage of the security benefits. And then, another feature is that, you can have multiple different pipelines, and so you can mix and match different protections as you see fit. So this is we believe to be a very interesting and promising architecture. And so how would hard mitigate things in the example program that we talked about before? So, here in this case, when this printf statement occurs here, and we're doing that, the compiler actually will compute the base position of A and B. And that signature, that set of instructions, that is what the hard architecture is going to key off of. So it is going to, use these kind of base address calculations that the compiler makes as a way to determine where A and B start and stop in their bounds. And so when the adversary starts typing in, A, B, C, D, F, G, H, I, J, K, L here again, and when we do this getS operation, the security pipelines, they're going to detect now that, hey, someone is trying to write into a space where we have object B, and it's going to stop that and throw an exception. And so in this case, again, the operating system can decide what to do with that, and here prevent bytes, the 9th byte BS from being overwritten. And so this is how hard would mitigate the buffer overflow type of attack. And how do we test our architectures? How do we prove that they're secure? Well, we did that in a multi-pronged approach. Before we even went into testing, we used formal methods to mathematically try and prove as best we can based on assumptions that our systems did what they said they would do. But we employed a number of other techniques to try and measure the security. One of the things that we did was we created a synthetic benchmarking tool we call TestGen. It's part of the BestBin effort. And that's kind of like, similar to a performance benchmark that you run on your computers or your phones today. It just does it for security. So it generates synthetic security tests for each of the CWEs that we aim to protect against. So we have, over 100 different sets of tests that we run on the processor to see how well the architecture protects and mitigates these hardware weaknesses that we've identified. Another thing that we did was we ran DARPA's first crowdsourced bug bounty program last summer. So we took 7 of our hardware architectures and we threw them up in the cloud and allowed pretty much anyone around the world to come and try and break them. So we had almost 600 hardware hackers, white hat hackers, security researchers, spend over 13,000 hours. So a long time over a 3-month period trying to break our systems. And these were systems that had old kind of janky software running on top of them. So we had our SIP processors, but we had old versions of FreeRTOS, Debian Linux, FreeBSD that had known CVE. So these are known vulnerabilities with known exploits. And none of those vulnerabilities or known exploits were able to be leveraged to compromise the system. So that was a tremendous and exciting result. Another thing that we did was we partnered with other outside organizations to do independent security evaluations of our system. So on the right here is a report that Microsoft Security Response Center, the MSRC, did, where they looked at our Cherry architecture, and they came to the conclusion that Cherry would mitigate 67% of all of the security patches that they had to do in 2019 for Microsoft products. And so that is just a tremendous, huge result that helps kind of really, I think, justify why we should have these types of architectures going forward. And so we've been trying to show how flexible SIF is. In FET, we had a number of different software systems that we had developed. So, server-based database applications, a medical records database, a voting registration database application. But we wanted to show people that, that this hardware is real and can be integrated into real things that we use every day. And so we actually took a car and we replaced the electronic control units with SIF versions. So we had a SIF-enabled infotainment system and SIF-enabled ECUs in the vehicle. We developed a variety of different cyber attacks against the vehicle, so we could, disable your anti-lock brakes or take over the driver assist system and take control of your steering wheel. And you can see we replaced the windshield with a curved LCD monitor and hooked this up to a driving simulator. And it's unfortunate because of COVID, we can't really have a lot of people experience it, but hopefully after COVID's over, we can open it up and have people come over and actually drive it and experience what it's like to be attacked with a cyber attack, and then see how SIF technology can prevent all of these attacks from happening. So I gave a talk about this at Black Hat. There's some YouTube videos you can Google and check out if you're interested. And then if you're planning to attend ERI in a couple of weeks, we'll be doing some deep dives into this hardware there. I wanted to let you all know that we have tried to open source as much of this technology as we can. So a lot of the infrastructure that we use for FET, the bug bounty, has been open sourced. Our security benchmarking software is all open sourced. Many of the hardware architectures are also open sourced, and you can go to GitHub and get access to those. Now that we know that our hardware is working, we want to actually build some silicon. So we are partnering with and working with the United Kingdom's Research and Innovation Organization, UKRI, on their Digital Security by Design program, where they are taking our SIF Cherry architecture and building a high-performance quad-core Neoverse N1 processor that will run Linux and Android and BSD. That hardware has already been fabbed, and we expect development boards to be available for evaluation in 2022. And so that's really exciting. And we at DARPA are also building hardware. So we are planning to build a dual core A55 ARM-based processor, more targeted towards the embedded kind of community. And we expect that hardware to be available for evaluation in 2023. And
just a second, 5 minutes left.
Thank you. And so I'm just, I think I just have a couple slides here. And so I wanted to present this opportunity to you all. We're looking for partners who want to, kick the tires on the hardware that we have, who have real world use cases. And so if you're interested in, trying out any of the hardware architectures that we've developed, if you want to test some of the silicon that we're building, please don't hesitate to reach out to me personally, or you can contact us at sith@darpa.mil, and we can look towards working together there. And just to conclude, we at DARPA we firmly believe that hardware and firmware is where we need to bring these protections. And if we start with a really strong foundation, then we can move protection and security up the chain, instead of kind of taking that top-down approach that we do today, which tends not to work so well. And with that, I'm happy to take questions and look forward to discussing things with you.
So with that, I will go to the next speaker. I'm also very honored that he accepted our invitation. Jason Fung is a known face to me. He is leading a team, a defense team, and in Intel, and he has been very passionate about hardware security and how we can use hardware security and in different programs in such a way that we are not only have an educational aspect, but also something that researchers can play with and see the challenges in practice. So Keith talked about memory protection and the SITH architecture and solutions. And indeed, Jason was one of the, so to say, main initiators of something that has become very big, and I am very happy to be a part of it together with a colleague of mine, JV from Texas A&M University. And Jason was the driving, so to say, force by providing Intel insights on hardware vulnerabilities, which is one step over what we knew with all kind of side channel attacks that was trendy and hype in the academic community. But it goes beyond that. It goes beyond that. Deep in the hardware, there are vulnerabilities that can be exploited by software. And one thing that Jason was doing in the last 3 years with his team is providing an immense amount of insight to the academia, but also those who are working with his team, and also to the world, because the competition, which is now known as Hackath event, it started 2018 with Hackath DAC, as a DAC is a systems, is an established systems conference, but now it is running in Usenix Security, which is a top tier security conference. It is running at Chess, which is a top tier embedded security conference, and it's going on, and hundreds of teams have been participating in that. And this is why I think Jason actually deserves a big award for his tireless working on this initiative, which is now one of the largest joint academic and industry initiative. And we are getting more powerful industry partners through Jason's wisdom and how to lead this. So with that, I think I don't want to talk too much about Jason's achievements now, because he needs to give his talk as well. And his talk is about turning art into science towards scalable hardware security assurance. Jason, the stage is yours.
Thank you, Ahmed. Thank you for the kind words. You can hear me well, right?
Yes.
Awesome. So good evening, everyone. Thank you for joining my talk tonight. And I know it is a long day for many of you. So as the last talk of the night, I promise I'm not going to show you formulas or charts in this presentation. And rather, for the first time, I have actually put some cute pictures in my external presentation to make a point, and you will see why. And I'm going to present to you some key challenges faced by the hardware technology industry And I hope you would walk away with inspirations on where you would invest cycles in your next set of research projects. And by the way, Ahmed, I don't know how you did this, but you seem to develop some foresight and line up my talk with Keith's talk perfectly well. And even before we share our topics with you, so kudos to you. So Keith shared with us efforts and opportunities in securing the supply chain to detect Trojans that are being maliciously inserted. Tonight, I'm going to share with you opportunities to help prevent vulnerabilities from being introduced by non-security savvy designers by mistake. Keith shared with us wonderful programs like Steve that employs hardware-based protection to minimize the risk of software programming mistakes. My talk will challenge you to innovate on solutions to help minimize the risk of hardware implementation issues. So again, I am the Director of Academic Research Engagement at Intel Product Assurance and Security. I oversee offensive security research of key technologies that power Intel's edge, communication, and data center products. One of my research interests is to automate vulnerability detection and remediation. And I'm thankful to be a part of a fantastic company for almost 23 years that creates world-changing technology that enriches people's lives. Many of us have picked up new hobbies during the pandemic, and it is no exception to my 10-year-old daughter. One day, she told my wife she wanted to learn how to draw chibis. If you have not heard about this Japanese term, chibi describes a set of specific style of cartoon characters drawn in an exaggerated manner with oversized head and shortened bodies. Drawing a chibi is not straightforward. There are concepts and techniques one needs to master in order to produce a good-looking drawing. For example, chibi characters are unique in the way the head, body, and legs of the character follow a certain ratio. When presented a drawing, it does not take a pro to observe if the ratio is done right. Even if you heard of chibi just now, I bet you can tell if a drawing is drawn in chibi style or not. As all artists are well aware of, the emotion of a character is often expressed through the face and in particular the eyes of a character. Chibi has a unique style in drawing these elements to reflect various emotions and expressions. Eyes are unrealistically large to show the cuteness of the character. Certain facial expressions are highlighted or exaggerated, while others are intentionally abstracted. Even an experienced artist that is skillful in drawing other styles of cartoon characters needs to observe these basic principles to produce a chibi-style drawing. While it may seem complicated, the saving grace is that there are many books and tutorials out there to show the know-hows. These resources help even the beginners to take a step-by-step approach to acquire the important concepts, understand the basic principles, master the essential tools, techniques, and best practices. They turn art into science. Just like recipe of a good cookbook, even a mediocre cook can follow the instructions to produce a delicious and professionally looking dish. And this is how my daughter learned and produced her first chibi drawing after a few hours of practice. And as you can tell, the head to body ratio still has some room for improvement, but the know-how makes it easy for her to deliver an art that previously thought impossible at her skill level. Building secure technology is no different. To many, reverse engineering a technology to identify flaws and injecting code to take over the control remotely seems to be a show of magic. And given there are so many ways to hack and break a technology, hardware security assurance seems more like an art than science. And we have seen the way the how-to guide helps its reader to learn and start drawing chibis without first becoming professional cartoonists. Likewise, there are more scalable ways where we can help engineers to build secure technologies without first training them to be seasoned security experts. To turn art into science for hardware security assurance, we can look for opportunities to help technology providers to understand important security concepts and principles, adopt industry best practices, and master proven techniques. And we should also find ways to expand the current toolbox. Today, I'm going to discuss some observations on why securing technologies, in particularly hardware, is harder than it seems. And once we understand these challenges, we then can look into a few starting points where industry and academic collaborations can work towards. We have seen a record number of reported vulnerabilities in 2020. Threat actors are not slowing down during the pandemic. In fact, according to IDC, over half of more than 160,000 new vulnerabilities documented over the past 2 decades were reported in just the last 5 years. From conception to retirement, technologies are exposed to a rising number of software and hardware vulnerabilities over their lifetimes. Unfortunately, despite the sheer number, majority of the reported vulnerabilities are recurring mistakes that have been reported before. In fact, if we take lessons from the software security industry, many of the issues affecting today's software, big and small, are common vulnerability patterns that are first discovered a decade or more ago. Just like what Keith mentioned to us earlier, the memory corruption issues has been discovered a while back. Hardware technology is no exception. Repeated mistakes such as effective practice is unavailable. And these are the most needed areas for security researchers to step in. And to understand what these common hardware weaknesses are, there are 2 resources technology providers and security researchers can look into. The common weakness enumeration maintained by MITRE, CWE, is a community-developed resource capturing patterns of security weaknesses often overlooked by developers. The primer has been around since 2006 with focus on software weaknesses only. Through a partnership with Intel last year, CWE has now been expanded to cover hardware weaknesses as well. Thanks to the contributions by the industry and academia organizations, hardware CWE now includes almost 100 hardware weaknesses patterns. Examples of hardware CWEs include common issues concerning circuit and logic design, security flows, debug and test, manufacturing and lifecycle management, privilege separation and access control, and more. Each CWE entry includes a description of the root cause, security implications, attack patterns, and demonstrative examples. It also offers guidelines on how the weaknesses can be detected, prevented, and mitigated. It is crucial for architects, designers, and verification teams to establish a firm understanding of each of these hardware weakness types and introduce measures throughout the entire security development lifecycle to prevent and detect similar issues from creeping into the technology products. The Hardware CWE Special Interest Group is working towards to release the top 12 hardware CWE lists to spotlight the most common repeated mistakes as observed by the industry. Its release will offer important insights to academic researchers on areas of concern that, if properly addressed, could make significant impact to the hardware technology industry. To appreciate how these common weaknesses manifest in a system on chip and how adversaries could exploit them for their advantage, going hands-on proves to be an effective means. A fun and educational option is to join one of the Hackett events hardware security capture the flag competitions mentioned by Ahmad earlier. Vulnerabilities introduced in the CTFs are inspired by real-world product issues. Hundreds have formed teams and participated since our first offering 4 years ago. Through learning by doing, participants gain valuable insights on how common hardware vulnerabilities could be detected and fixed. The next event will be at the Design Automation Conference, DAC, in San Francisco in early December. You can sign up at hack@events.org. This is our 4th time partnering with DAC to offer the competition, and we have introduced a number of new capabilities that will appear for the first time at Hack at DAC. And check with our friend Ahmad for an insider scoop if interested. As discussed earlier, the recurring mistakes shown in hardware CWE keep coming back year after year because the industry does not yet have the means to successfully prevent or detect them at scale. While developer education and adoption of best practices are very important, hardware development teams can also benefit from electronic design automation EDA solutions that are purposely built to assist users to develop secure technologies. Most tools available today focus on detecting vulnerabilities after introduction. Yet, it is not uncommon to see designers attempting to fix a security issue while introducing a new one by mistake. Perhaps a more forward-looking question we should all ask is, can common security mistakes be prevented at all? How would the next generation EDA solutions look like? How would such solution make it impossible for development teams to introduce security issues in the first place without the users first being trained to be a top-notch security expert? I'll start off with a set of design principles that I believe an effective EDA solution should support in order to deliver the best user experience. These serve as innovation opportunities for the industry to consider. I'll then discuss a set of intelligent capabilities that a security-aware EDA solution should offer. They represent a set of initial open research problems that the academic community can help tackle. Let's start off with design principles. The next generation EDA solutions needs to be easy to learn, easy to set up, easy to use, and easy to use correctly. It should enable users to complete assurance tasks with expert quality without requiring them to be first trained to be a security expert or first master a new complex language like formal. Its interface should be intuitive. Its output needs to be clear and prescriptive. It leaves no room for users to misinterpret a failed or inconclusive test as a pass. It should not give a false sense of assurance when verification coverage is insufficient. It should not flood users with a long list of potential findings and let users sort out the false positives. In addition, the solution should offer insights, not just data, when and where most needed to encourage secure by construction practices. In other words, relevant data should be translated into insightful, easy to understand metrics. Metrics should lead to actionable prescriptive guidance that users can follow to improve their designs. For example, showing verification coverage of 53% is just the beginning. Providing guidance on what tests to run and what parameters to tweak could be more actionable to help users to complete the verification coverage. The automation solution should cater to users of all levels of expertise. It should be ready to run out of the box with minimal per user and per project setup. Entry-level users can get values right out of the box with expert-created content covering mainstream assurance areas. Yet, it should also offer extensible interfaces or programmable engines to enable advanced users to fine-tune the tool and create content specific to their proprietary designs and their specific security requirements. Perhaps the biggest challenge of today's solutions is their inability to understand designers' intents. Design languages such as System Verilog do not make it easy for designers to convey if signals, registers, modules, interfaces should be considered by the tool as trusted or not. Without a good understanding of the security requirement, tools often run blind in its evaluation. This leads to a high number of false positives, false negatives, or both. Without switching to a new design language or augmenting the existing one, there are still opportunities for a security-aware solution to learn about designers' intent over time. For example, just like a human reading someone else's code and learn how it works, the next-gen solution can take cues from user comments, naming conventions, or design patterns in the LTL and start making assumptions. As a user accepts or dismisses a reported finding, it offers valuable insights to the tool to calibrate its assumptions. In short, there are opportunities for a smart solution to extract designers' intent from the RTL and feedback from its users, and then offer more accurate security guidance in return. In light of the design principles that we have just discussed, to proactively prevent common security mistakes from creeping into the design, let's discuss a set of intelligent capabilities that security-aware automation solutions should offer. First, it has the ability to guide users to make design trade-offs that balance security and functional considerations such as performance, power consumption, and die size. To achieve that, we first need a way to characterize security robustness of a given design. what are the common sets of metrics that can provide such insights? Note that while general hardware designs can be vulnerable to a broad spectrum of threats and security concerns, depending on the security objectives for a given product, only a subset of them would be relevant. How does the automation solution know which ones are relevant? How should the relevant metrics be presented as insights to help users embrace security as a top-of-mind priority rather than an afterthought? How would they be translated into actionable guidance that enables users to make important security by design decisions? Second, a smart security-aware solution educates users proper design for security best practices on the spot when security-sensitive design decisions are being made. While classroom learning is one thing to acquire such knowledge, seizing the on-the-job moments to raise user awareness can help reinforce adoption of important design practices. The next generation EDA solution can play the role of a virtual security consultant, assisting users to build a secure product every step of the way. The challenge is, how can it understand the intents of the users so that it can offer security recommendations that are timely, accurate, prescriptive, but not overly intrusive? Third, an intelligent security-aware solution detects security issues introduced right at the coding time and offers users reliable options in addressing them. Word processors have been offering valuable help to users by highlighting and correcting spelling and grammatical mistakes in line when documents are being edited. Smarter versions offer options to improve the stylistic form of writing, and some even manage to analyze the context of the document and make suggestions to complete what the users are about to write. How would we develop a smart solution that would alert users as they are about to introduce security vulnerabilities into their design? In addition, how would we enable such solution to offer reliable mitigations to correct them? When there are multiple ways to mitigate a specific concern, how would it identify the best option, not only optimized for security, but also one that meets the circuit timing constraints with the least power consumption and gate count overhead? Not all security properties can be verified by analyzing the design statically. Hardware simulation and emulation often are required to monitor runtime behaviors essential in identifying weaknesses involving race conditions, interactions with firmware, security flows, and more. Today, the burden to identify what tests to run and what parameters to use falls on the shoulders of the development team. It is an open challenge even for seasoned security experts and verification experts to verify all security properties without wasting valuable test cycles on redundant test cases. As the fourth capability, a smart security-aware solution can play a key role in analyzing the design, suggesting the minimum set of verification tests required in order to provide a given coverage guarantee. No system is perfect. Even for a smart EDA solution, it is only fair to expect it would miss security issues that it intends to find, or provide misguided recommendations to users at times. Lastly, an intelligent solution needs to learn continuously from the user base to improve its accuracy and quality over time. Likewise, users are not always correct. They may feed the tool incorrect information. Conflicting feedback from different users could also be received due to differences in their preferences and priorities. How to apply artificial intelligence to identify improvement opportunities from crowdsourcing feedback could be an interesting line of research. We have discussed the importance of taking learnings from the hardware weakness patterns that designers have repeatedly made by mistakes. We have also discussed how an intelligent security-aware automation solution could help users avoid making these common mistakes, and the open research problems that the industry and academia can collaborate to drive necessary breakthroughs. Now, let's look into how advancements in systemic mitigations could open up new possibilities for hardware designers. With software being the prime target for attack, Security research community in the past decade has made great strides in hardware-based solutions that produce the confidentiality, integrity, and reliability of software workload running on top. As Keith has shown in his talk earlier, hardware-based systemic mitigations, like the one shown in the DARPA SIF program, help to significantly increase the barrier of attacks and minimize negative impacts of software exploitations, making practical attacks much harder to succeed even for the most determined adversaries. While software developers may continue to make common programming mistakes, like unvalidated inputs, they could result in memory corruption. Many of these are no longer exploitable when hardware-based protections are present. Now, we need a similar approach, a similar research investment to help cover the back of hardware designers. In parallel to the relentless effort to keep hardware weaknesses out of the designs, novel systemic mitigations can also help to make escapes difficult for adversaries to exploit. Let's walk through a few research areas that has the potential to offer effective building blocks for hardware designers to build secure technologies. Again, this is where academic and industry research collaborations comes in. Electronics that are vulnerable to faults could result in errors in computation, leakages of sensitive information, and bypass of security mechanisms like access control and secure boot that help to protect the overall system. Circuits that are resilient against physical attacks offer a level of assurance for the computing logic built on top. The added assurance at the circuit level helps to free up the mind of hardware designers to focus on their innovations. To help improve silicon resilience and reliability, security researchers can offer in-depth studies to understand the intrinsic properties of silicon characteristics that make a device more vulnerable to faults. Circuit-level innovations in detecting when a device is operated outside of the rarefied range. Novel microarchitecture and architecture techniques to recover from failure conditions. Self-healing mechanisms that help prolong the lifespans of electronics after attacks. To tie all these together, we need design tools that automatically synthesize resilient circuits without end-user supervision. It is similar to how C compilers today generate binaries for software programs that are resilient against memory corruptions. They automatically incorporate any available mitigations offered by the compiler, operating system, and hardware platform. Telemetry collection has been a common practice in the software world. During software installation, users are often asked to provide permission for the applications to collect data for diagnostic and product improvement purposes. Likewise, hardware telemetry can provide crucial insights to designers to help root cause complex issues reported in the field, detect attacks in real time, accelerate development of effective mitigations that scale across systems with different configurations. Along with big data analytics, discrepancies detected across systems can also help reveal early signs of reliability issues or facilitate timely recovery of emerging attacks. While collecting as much data as available seems to be a preferred approach, some data may expose the identities and the behaviors of the system users. Research learning can point hardware designers to an optimized set of hardware telemetry that are both effective and privacy preserving. Many hardware technologies available in the market today are yet to offer a robust in-field update solution. This is especially true for chips used in a resource-constrained environment such as IoT devices and sensors. For a good example of this, look no further than the home automation technologies. During the pandemic, I have installed a variety of connected devices in my home, including a smart thermostat, doorbell, router, as well as IoT cameras, wall plugs, and light switches. The growing and fragmented smart home market netted me 5 different smartphone apps to manage a dozen smart devices from various IoT vendors. Throughout what became an overwhelming user experience, I noticed several hardware security considerations. Many smart devices cannot perform remote update on their own without the associated smartphone app or smart hub serving as a middleman. In addition, The discovery of available firmware updates would not be automatically initiated unless users first open each of the vendor's apps. The high-touch user interactions presents a practical roadblock to facilitate timely deployment of critical security patches. For devices that have direct internet connections to perform updates on their own, if not designed or implemented correctly, the update mechanism could present a convenient attack surface for adversaries to introduce malicious codes to the devices. Adversary can then use the compromised device as launching pads to attack other systems sharing the same network. The landscape of remote update capability in hardware platforms today is similar to their software counterparts about a decade ago. Robust mechanisms is either missing or fragmented across technology providers. To keep up with the emerging threats and evolving product requirements, infrastructure that offers proactive updates covering all components of a system is essential. Rather than having each vendor inventing its own infrastructure and protocol, a universal in-field updates mechanism backed by industry standard that supports heterogeneous architectures and devices could be a more viable option. By pooling the best minds across the ecosystem, the standardized solution could be more well thought out and more resilient against adversaries, which helps to gain trust from the consumers. Without the need on large upfront investment, technology providers, big and small, can all participate and adopt a standardized solution, ultimately leading to a better user experience. To sum it up, I have highlighted several paths which address key challenges faced by hardware technology providers today. While securing hardware technologies may seem to be an art best reserved to the most skillful, to enable the industry to scale, there are plenty of opportunities that academia and industry can join hands to turn some of the art into science. At the beginning of my talk, we have discussed the way how to guide help its readers to effectively learn and start drawing chibis, all without first training them to become professional cartoonists. The essence concerning the art of chibi drawing is clearly broken down into concepts, principles, techniques, best practices, and tools. For hardware security assurance, we have discussed opportunities following a similar approach. Resources like MITRE's Hardware CWE and Hackett Event CTFs educate technology providers essential security concepts, security by design principles, and proven technologies to detect, verify, and remediate security vulnerabilities in their products. It offers insights to researchers on the most challenging problem yet to be addressed. Security-aware automation not only serves as a smart assistant to help accelerate the work of hardware designers while preserving security vulnerabilities from creeping into their designs. When it is done right, it also helps to reinforce its users secure by construction best practices and offer relevant techniques in a just-in-time manner. Systemic mitigations expand the toolbox of hardware designers as they adopt proven security robust building blocks into their designs. Industry best practices are incorporated seamlessly to help secure their technologies. Hardware security is easily one of the most challenging technology disciplines today. Adversaries are constantly looking for new weaknesses. Evolving product usage models and security regulations can be moving targets. The process for deploying hardware security updates to systems in the field is lagging behind their software counterparts. Yet, user expectations for security have never been higher. By the same token, hardware security is easily one of the most rewarding technology disciplines today. Hardware technologies that are secure and trustworthy are instrumental to improve lives and change the world. Security could not be a more worthwhile and valuable focus, and I strongly believe collaborative research efforts between industry organizations and academia can accelerate our ability to build a trusted and secure foundation for world-changing technologies to enrich every person on Earth. Thank you.
So with that, we come to the, so to say, closing. I don't want to make it long. I just want to thank all the speakers who are still remaining in this conference. Without them, we don't have this amazing content and information also for further research. It's very useful for not only for our colleagues, but also for PhD students and postdocs and other young researchers who are in this who were in various talks. And I also want to thank our attendees who were very brave, and many of them, they just were at least online. I don't know if they were listening, but I hope that they were listening. Some of you have very good questions, and speakers always are happy when they get questions to their talks. So now we are just ending it. I hope that next in 2 years we still have a crossing conference and the project goes further. I will definitely organize other conferences in this format and physically, hopefully. And I wish you safe day and nice weekend, and stay safe. And I hope that we can travel to everywhere soon and take the life as it was before, although I don't think so that is going to be as before, but with some care, we may get back to the normal life. Thank you very much. I also want to thank Lisa and Catherine again for their tireless working. I know that they are extremely tired in background, always keeping keeping the time. I wish you all a nice life until the next time. Bye.